Howdy. Good morning, everybody. Thank y'all for being here. Hope everybody's doing well. Hope y'all had a good weekend and that your Tuesday and your week is off to a good start. Um, Today we are going to be talking about something called two-group diffusion theory, getting into the question. Oh, shit. I thought I did. One sec. If not, I could fit there real fast. Here, let me tell you what. I have a quiz that I was gonna pass out to y'all, so let me get y'all going on that, and I'll get the slides set up while y'all are doing that. Would y'all mind clearing your desks? Only thing you'll need is a pen or a pencil and something to write with. So please keep them face down until everybody's got one. Here's just like a stat. You can pass those out. Please keep them face down until everybody's got in the room. Please. There should be enough. Everybody back there got one. Did I give enough pieces out? Okay, cool. All right, y'all are good to get started. Good luck. Let me know if you have any questions along the way. Got just about one more minute to go. Alrighty, that is the end of time, people. If y'all wouldn't mind, making sure you got your name on there, and then stopping any writing and passing those papers forward. You guys, hopefully that went okay. Um, I am a little bit behind on grading quiz two because I basically spent the whole weekend making sure everything was set up for this week as well as our exam. So I guess as we get into it for today. Oh, by the way, if you were looking for those slides, my apologies. I thought that I had put them here, but I forgot. But they're here now. So if you go in our drive, the blank slides for lecture five are there. Um, in our let's just jump into our presentation for today. And I guess I'm probably going to end up jumping back and forth because actually, and I am, because the first thing that I really was going to talk about is our exam review materials. I sent out an email about this, but all of this stuff is in the drive too. So just friendly reminder, a week from today in class, we have our first exam. It's going to be similar to our quiz format in that no notes, no electronics, closed book. Um, on Google Drive, so let me show you where I'm talking about. If you go in our drive under exam materials, there's the exam one guide, and then there's the exam one formula sheet. So this formula sheet is going to be provided to you on the exam. Um, this, in my opinion, is a thing where because I'm providing you the formula sheet in advance, it is a good idea to make sure that you are like reviewing the formula sheet. You're going to have homework three that's posted today. That's going to be due a week from today. So that's the other thing is that if you look at the scope of our material, it covers chapters one through four. We've already basically covered chapters one through three, and then this week, lectures five and six, we're going to focus on chapter four. Um, everything on, so whatever we get through in chapter four, that's going to be the scope of our exam. So like as you're doing the homework three, using this formula sheet is probably a good idea so that you can practice making sure that you know where things are. That way, the formula sheet will be more useful to you when you actually take the exam. Also, that way, whenever you jump into the exam for the first time, you're not going to be like overwhelmed by all the formulas. You'll kind of be comfortable with where things are, so you won't have to spend time like analyzing the formula sheet because hopefully we've already been like preparing for it and have a decent understanding of what's on here before we go into the exam. The exam one guide is here. It tells you kind of what the scope of the exam is going to look like. So it's going to be structured kind of similar to our homeworks, where like the first half is like concept-based questions. So those could be multiple choice, those could be short answers, kind of like what you were just seeing on the quiz. And then the second half is going to be like some calculation, type problems and then some derivation type problems. I'll also give you guys a couple bonus points. So like the overall points will be out of 100, and that's where all the points come from. But then there'll be like a one or two bonus questions at the end. So in terms of what to prepare, oh, question. Yeah.
What's a question? Is that like the first part of all my?
Right. Yeah, those are like concept-based, open-ended, short answer type questions.
Like the rest of, where it's like backward.
Yep, exactly.
How, do we have a list of the derivations like the asked?
Mhm. Yeah, so that's all in this guide. I was just going to talk kind of over generally about what the exam is going to look like, and then I was going to give you guys this exam guide to kind of focus your studying. So this lets you know what the scope of it is, which I kind of already talked about. Similar to our quizzes, but you'll have a formula sheet that I just showed you. It's covering chapters 0 through 4. In chapter 3, there is stuff about numerical methods for the diffusion equation. We didn't talk about that. Don't study that. That's not going to be on the exam, any numerical diffusion stuff. So that's section 3.3 in Svetkov's notes. That's not going to be on there. And then I'm anticipating us being able to get through 4.1 and 4.2. So that's my anticipated scope of these questions for chapter 4. And that's what we're going to talk about this week. So if you go through the rest of this scope, it tells you like topic by topic, page number by page number, the things. And this is all based on the page numbers in the Dr. Svedkov's lecture notes. But my slides kind of follow a similar order. And so as you go through this, it'll tell you what kinds of concepts to focus on. It'll also tell you to make sure what kinds of derivations you're aware could be on the exam. So, I mean, this has a bunch of those. It basically just goes through everything that we've talked about, covers the main models and concepts. And then I threw in a bunch of study questions. These are designed to get you thinking and to make sure that if you were to answer all of these questions, you're going to have like all of the concept pieces down to be able to answer basically anything that I asked you about. This goes very far. I mean, like you can look at some of these terms are basic structure of an atom. It goes back to like chapter 0 all the way through what we covered so far. So in terms of what I would focus on, I would focus on the homeworks. I would focus on the derivations that I'm talking about here in this document, and quizzes. Basically, focusing on the stuff that we've done in class and that you've done on homeworks. My feeling is that if you are really understanding those things, then when you come and see the exam, it shouldn't be too much of a surprise. So that is the scope. And if y'all have any questions as you're going through your reviews, feel free to let me know. We'll have our normal help session on Friday so that if you are having questions on homework 3, or if you want or needing any, if there's anything you're wondering about in terms of preparing for the exam, well, we can talk about that. So, thank you. That would be way too much, Don. Sorry about that. Dr. Mariano is going to be observing the class. Just pretend like he's not here. Okay. Um, so last time we were here, we were in the middle of almost finishing chapter 3. So I wanted to talk a little bit about that before we got into the chapter 4 stuff. So last time we were here, we were talking about multi-region diffusion. We did one group diffusion where we had these very simple one-region reactors that were very simple. A real reactor is a multi-region system. So this is a picture of like a typical reactor core. This is a picture of what we would call a fuel element. And then this is a picture of a fuel assembly. When we talk about fuel, that's like fissionable material in our reactor. A fuel element is the smallest unit of fuel. So it contains these UO2 fuel pellets that you've seen. It contains some cladding that kind of contains those fuel pellets. There's springs that are designed to keep all of those pellets nice and close to each other. So this is what a fuel element looks like. A fuel assembly is just a collection of fuel elements with these spacer grids and these things that basically keep all of these fuel elements in nice straight lines and make sure that they don't vibrate and things like that. A thermal reactor will have a moderator, which is made of some low atomic number materials that is designed to help slow neutrons down. Um, we talked about reactors having very high fission rates. They produce a lot of heat. You need coolant to make sure that your reactor's temperature doesn't go above what it should be. So you have coolant in your reactor to make things to stabilize your temperature. You've got control rods, which are absorbing materials that make sure that if you ever need to shut your reactor down, you can throw a lot of these absorbing materials in your reactor. They'll absorb all of your neutrons and they will stop your chain reaction from continuing. So this is like the things to keep in mind when we're talking about a multi-region system. Real reactors have multiple regions, so we're getting closer to understanding what a real reactor looks like when we go from one region diffusion to multi-region diffusion. Um, and also, so the core is going to contain all of these elements 1 through 6. You will have usually a reflector, which is designed to make sure that you're preventing neutrons from leaking out of your system. It is also helpful because the reflector protects people who are working at the reactor from the radiation field of your reactor itself. Reactors are usually made of low microscopic absorption materials so that they don't absorb neutrons. They just make them scatter, hopefully bounce back into the reactor and make a new fission happen. And then reactors have shielding that is also designed to protect workers and the public from our radiation in our reactor. So I know that I've mentioned terms like this before. I wanted to make sure I was defining all of them so that if we were confused about like what's he talking about when he says moderator or cladding or things like that, that we have some picture for what that looks like. So last time that we were here, we derived the time-dependent one-group diffusion equation. We can write this equation for multiple regions by using a superscript I that is talking about what we have in each region. Within each region, we assume that the material properties for that region are constant. So they vary from region to region, but within a specific region, the properties are the same. Um, to solve this partial differential equation, we need conditions to apply. Those are boundary conditions, initial conditions, interface conditions, and physical realizability conditions. We saw all of these when we did one group diffusion. The interface conditions are the new thing for multi-region systems because as you go from one part of your reactor to another, the scalar flux through your whole reactor is a continuous function. And that means that as you go from one region to another, you have to make sure that the flux in one region matches the flux in another region. And we do that by making sure that the flux is continuous. We make sure that there's continuity of the scalar flux at our interface location. And we also make sure that there's continuity of the normal component of the current. And if we get our general solutions and we force these interface conditions, then the solutions that we ultimately get will have a smooth form and they will match both in terms of their derivative and their function value at the interface. So the next thing that we did is we derived a criticality condition for a simple system that had a core surrounded by an infinite reflector. That's what we did last time. And these were the general steps that we went through to get this criticality condition. If you have a multi-region system, you can't just use like a simple formula for K effective. We actually have to do a little bit of deriving of what that formula looks like. And these are the steps. It's basically the starting point from that, what we saw on the last slide, that you have your equation, you have your conditions, you simplify and you find the general solution to each region. You simplify the solution using either boundary conditions or physical conditions. Once you have those general solutions that are simplified, you can apply your boundary conditions to match your solutions in each region. If you do that right, you should end up with some linear algebraic equations that can be solved for the unknowns that are remaining, the constants that appear in your general equations. Um, from there, we're going to go into matrix math, and we're going to hopefully recognize that if we can get the system in a form that looks like this, where we have a coefficient matrix times the column vector of our coefficients all equal to a 0, then this system will have non-trivial solutions if the determinant of that coefficient matrix is a 0. So once you get this matrix form, you can take that determinant, set it equal to 0, and then that will give you the criticality condition for your reactor. So we did all of this last time for a problem, and I just wanted to make sure we were spelling out what those steps are, because you're going to do this on homework 3 for some more complicated systems. Questions?
Homework, we're gonna do this.
So the homework, yeah. So homework 3 is gonna is gonna start today, and it's gonna be due Tuesday. So that, and I'm glad that you mentioned that. It's a challenge with the summer class where things happen fast, and so I am doing a homework every week. But part of the other complication is that we have Juneteenth that comes up that same week, so we like lose a day. So in terms of homework 3, my suggestion would be do homework 3 as soon as, I mean, always do it as soon as you can, but you need to have homework 3 done before you come into class on Tuesday, right? Because the exam 1 is going to cover what you see in homework 3. So that would be my recommendation is do homework 3 before you come into class. That way you've practiced the problems and the derivations that you might see from the chapter 4 homework 3 material. I apologize that we are having a homework due the same day as our exam. I could have made the homework due earlier, but I don't think that would have made anyone happy either. Um, and so this is just basically a review of the math and the equations that we got last time. So when we applied, these were our general equations. Does anybody remember? So we had region 1, which is the inner core, and we had region 2, which was the reflector. And these equations look very similar, but we have a bm squared in our equation for region 1, and then we use a b effective for region 2. Does anybody remember why we used b effective for region 2? Yes. Yes, perfect. There's no fission, and so your Bm is like a nu F sigma F minus a sigma A over the diffusion coefficient. But if you don't have fuel, then you don't have fission. So those fission cross sections and the nu F is 0. So overall, this is like your material buckling, but for a region that has no fuel, and that's why we call it B effective. Um, and so we have general solutions to these regions. We applied the interface conditions to get equation 1 and 2. And from there, we recognized that we could write those equations as a matrix in a matrix form that looked like this, where the column vector is our vector of unknown coefficients. So we take the determinant of this coefficient matrix, set it equal to 0, and that gives us this equation right here. This right here is where we stopped last time, and really, that's most of the work of the problem. Once you have that equation, in practice, what you would do is this equation, everything in this is just material properties. Like Bm is a material property, B effective is a material property, and the diffusion coefficients are material properties. And then R at the interface is the value of the like radius of our inner core. So this equation just has material properties and like reactor dimensions. What you would do in practice is you would play around and you would adjust your materials until you had values of all of these constants that made this equation be true, that made the left side equal to the right side. And if you picked all of these coefficients, all of these material properties, and the radius such that the left side equals the right side, then all of those numbers are the properties that make your system critical. And once you know what values of like Bm and B effective and the diffusion coefficients that give you a critical system, you can go back to your equations 1 and 2, and you can figure out what these unknown constants are. And also from equation 1, you can express the constants in terms of each other. So by expressing expressing C4 in terms of C1, it allows us to write our general solution for each region in terms of just one constant. Um, and so this is what our solution is going to look like for this system that has a core in the middle and then an infinite reflector. And this constant C1, you could find that if you knew, for example, the reactor power, or if you knew some other property of the reactor, if you knew like a reaction rate, you could use that information to find the unknown constant. So that's just like one extra step that you would have to do to go from what we did in class to getting this solution. So we did this problem. We didn't really talk as much as I maybe would have liked to about why we care about reflectors in the first place. So I wanted us to imagine that we've designed two reactors. Both of them are critical reactors, and they're using the same fuel, so it's like same BM, same material properties. The first reactor is just a bare core that has a radius of R1. And then the second reactor has an inner core of radius R2, but then we take that core and we surround it by a reflector. And the question is, how do y'all think the inner radii of these two systems will compare? Which one is going to be larger, R1 or R2? R1, we think R1 is going to be larger, right? And why do we think R1 has to be larger? Perfect, right? In the bare reactor, there's nothing around the reactor to stop its leakage. So if this reactor is critical and the other reactor is critical, but it has a reflector around it, the reflector reduces the leakage, and that means that this inner core can be critical with a smaller radius. So R1 is going to be bigger than R2. That is to say, the non-reflected system has a larger core. And hopefully that makes sense because when you're adding the reflector, you are effectively, like we just said, you're reducing the amount of leakage from the system. Addition of the reflector reduces leakage. Um, and what that effectively does is it allows you to design a core with a smaller volume. So it allows for smaller core volumes. So that's one like immediate benefit of a reflector. Like uranium costs money. We have to design some core. Well, we can actually design that same core to be critical if we just made the core itself a little smaller and then put a reflector around it. Um, in nuclear engineering, so there's this difference between the radius of our reflected and our non-reflected system. The difference in those two radii, we give it a name, and that is called the reflector savings. And they use a little delta. Let me write a better one. They use delta as the symbol for reflector savings. And delta is very simple. It's literally just the difference between these two radii. It's the radius of your bare system, which is going to have a larger radius, minus the radius of your reflected system, which is going to have a smaller radius. So conceptually, that's what we talk about in terms of the reflector savings. That's as most as I'm going to ever ask you about in terms of reflector savings. In the book, they go through some calculations involving that, and I think we're going to skip those calculations. Um, so this reflector savings, it's a difference between two radii. So what kind of units does it have to have? Centimeters, or it's going to be like a length, right? We'll just say it has units of length. And it's basically telling you how much your dimensions can be reduced by the fact that you are adding a reflector. So those are some good benefits of reflectors. And once we have that understanding, I think there was only a couple more things I wanted to say about just like kind of practical engineering stuff involving reflectors. Um, so in terms, kind of like what we were just talking about, it allows you to reduce your core volume. Another way to think about it is that it allows you to reduce how much fuel you need or what your fissile fuel enrichment has to be. So it can allow you to reduce your enrichment as well, like your percentage of 235U that you use in your fuel, um, for the same reason. So that's another way that you can save money if you use a reflector. Um, when we talk about reflection, if a neutron reflects off of something, what kind of a reaction is that going to be? Scattering reaction, perfect. So reflection is a scattering reaction. And when a neutron scatters, ideally you make your reflector out of a material that is going to force the neutron to lose a lot of energy in that collision. And then, so neutrons are being born from fission. They're going and they're diffusing out from your core, and then they hit this reflector. And once they hit the reflector, it causes them to be scattered back into the core. So in that scattering event, they lose energy and they go back into the core. And if they lose energy, how does that affect their chance to fission? It actually increases the chance of fission, right? It increases their chance to fission when the neutron has a lower energy. So we could say fission in the fuel. And hopefully that makes sense because we talked about and we saw like the microscopic cross section for uranium-235, and we saw that as energy was lower, the fission cross section and the total cross section were higher. So that is helping us hopefully appreciate that these in like a fissile nuclei like U-235, the fission is more likely if it happens from a neutron that has a lower energy. So the reflector reduces the leakage, but it also brings our neutrons to a lower energy, which makes them more likely to cause the next fission. Um, and as a result of these neutrons getting scattered back into our reactor and causing fissions like near the outside of the reactor, what that does is it actually flattens the overall flux profile. So it will flatten the flux profile. And we can kind of see that in these two figures, that the top figure is what your reactor core flux distribution would look like as a function of position if you did not have a core. So at this interface, you just have vacuum on the right-hand side. And this is a plot of the same reactor, but you've added a reflector to make it be critical. So notice the core region has a smaller radius than the when you have a reflector, the core has a smaller radius than the non-reflected system. Notice that the thermal flux doesn't just continue to drop as you go out of the system because now we have this reflector here. And as you go into the reflector, your neutrons are losing energy, they're being thermalized, and then they're being sent back into your reactor. So as a result of adding the reflector, your flux doesn't drop to zero at the outside of your core. And that allows some of these neutrons to slow down, to scatter back in, and as a result, the overall flux profile is flatter. Also, what this ends up doing, if we look at the height of this P average, which represents the average power of the reactor, because you have less neutrons leaking, and you have more fission in the outer part of your system, overall, it ends up increasing the average power of the reactor without really changing much about what the maximum flux is going to be. So adding the reflector increases the core's average power without changing its maximum power density. And that's what these two figures are trying to show. If you look at the peak of like where this maximum is, the maximums are basically the same. It doesn't change what that peak flux looks like, but it does change the distribution overall. It kind of comparing these two curves, this profile is a little bit flatter, like it doesn't just fall off. And as a result of this, you get more power out of your reflected system, more average power. These are good graphs to know. If I were to ask you to like sketch what the flux in a reflected versus non-reflected system looks like, that would be a good graph to show me. So with all that being said, that's kind of like where we're going to end with the one group diffusion discussion. Um, that's kind of the main focus of chapter 3 for bare systems and multi-region systems. Um, if your reactor is large and homogeneous, then fixed law is going to be okay. But ultimately, we want to do better than fixed law, and we can do better than fixed law. The way that we can start doing that is to consider more in detail the distribution of these neutrons in terms of their energy, as well as, and like we've already considered how they distribute themselves in terms of space. In chapter 4, we're going to see more about how they distribute themselves in terms of energy. And that's going to help us better understand our reactors. That's going to get us closer to our goal of understanding how nuclear reactors work and why they do what they do. So instead of having one giant energy group and treating that whole group as having like an average energy and an average speed, which is what we did in one group diffusion, we're going to say, let's break this whole energy axis up into a bunch of little groups. Each group is going to have a certain range, and then we can do our analysis on a particular energy group. And that's going to give us more insights into how energy plays a role in our fission reactors. And in terms of just like what the principle would be, that if you could, it's kind of like if you go from having a bunch of points to having like a continuous function, that if you go from some discretized thing to some continuous thing, you can like learn more about it in more detail. So it's like if we started with 5 groups and then we went to 10 groups, we would get a better resolution. And then if we went to 100 groups, we would get a better resolution. So if you make your number of energy groups sufficiently small, then you can start to predict and characterize what's happening within that group. And that process, that's basically multi-group diffusion. That's how most reactor designers design cores. Like if you take a NUIN 418, which is the core design class, you'll use a program called Casmo, and that's under the hood. This is what Casmo is doing. It's solving multi-group diffusion equations. So we're going to learn kind of some of the theory that is going to be under the hood in a lot of actual real reactor design. And the way that we're going to start this is just considering 2 groups. One group is a thermal group and one group is a fast group. So this is kind of like a review, but it's helping us appreciate, and I want to emphasize why we care about energy dependence in the first place. And this is what I was talking about in terms of, this is the U-235 cross sections, the total, the fission, and the capture cross section. Notice that as the energy decreases, as we go this way on the energy axis, these cross sections increase. So if we can make our neutrons have a lower energy, it's going to increase the chance that they have some kind of fission reaction. So energy plays a role in our cross sections, as we can see in this plot, but also recall that the reaction rate density is going to look like a cross section times a flux. So that means that if the cross section depends on energy and the reaction rate density depends on the cross section, then the reaction rate density is also going to depend on the neutron energies. And as we can see in this plot, that probability, if the fission cross section increases at a low energy, that means that the fission reaction rate increases at low neutron energies too. Every reactor that's producing power in the United States is a thermal reactor, which means that most of the fissions are caused by neutrons that are at thermal energies. And when we did homework 1, you had that problem where you did like the E equals 3/2 kT calculations to predict what's the energy corresponding to a neutron at room temperature. And that is the thermal neutron energy. When you did that on the homework 1, you should have gotten something about 0.025 eV. That represents the expected energy we would have for a neutron that is in thermal equilibrium with its surroundings. So we know about cross sections, we know about reaction rates. The other thing that we've talked about, but maybe we didn't appreciate, is that the neutrons that are born out of fission also have an energy spectrum. And that's what this fission spectrum is. That's what this chi of E is, the fission spectrum. In this first graph, it's the red curve. And I'm sorry that on this graph, it's the blue curve. So this graph is this graph. And in the top graph, it's showing chi. It's also showing, chi is a probability density function. So it has units of inverse energy, and it tells you about the probability per unit energy of a neutron being born from fission with a certain energy value. So this plot down here is the exact same plot. So this is also chi of E. But now the neutron energy is on a log scale, and that just makes it easier to see what's happening in the graph. We can see that at an energy of 1 MeV, our graph almost peaks. So 1 MeV is like the most probable energy of neutrons emitted from fission. And as the energy gets lower, the probability of a neutron being born with these energies gets smaller, right? So if we look at this plot of chi of E, hopefully what we can appreciate is that most neutrons in our reactors are born fast. Um, if we say that thermal is like 0.025 eV, or maybe we'll set the cutoff for thermal at 1 eV, most neutrons, like 95+% of neutrons, are born with energies above 1 eV. So most neutrons are born fast, but our reactors are thermal. Our uranium-235 likes neutrons that have low energies. So most of our neutrons are born fast, and then we need some way for them to lose energy so that they are more likely to cause a new fission. So we have to figure out some way to slow our neutrons down to get them from their fast group where they're born into the thermal group where they're more likely to make a new fission happen. So what we want to do is we're going to assume that our flux depends on energy, but instead of using an energy variable, we're just using two energy groups. And within those groups, it's almost like we're doing diffusion, but just in a certain group. So within the thermal group, we're going to look at what are our gain and our loss mechanisms. In the fast group, we'll look at the same thing. And then this will give us this will allow us to characterize what's happening within each group. So group 2 is what we are going to call the thermal group. Group 1 is what we're going to call the fast group. E0 is so this is the boundary or the energy range of our fast neutrons. The fast group goes from E1 to E0. So E0, that's our max. And E2 is going to be the minimum. I know that that's kind of confusing, that the indexing almost goes backwards from what you would expect, but this follows the lifetime of the neutron, which is that the neutron is born fast, and then over its lifetime, it will hopefully lose energy. So that's the rationale for why they do this backwards indexing on the energy groups. You're starting fast, and you're ending up thermal when you get absorbed to make a new fission. So if we have these two energy groups, what we want to think about is within each group, what are our kinds of productions for neutrons and what are our losses for neutrons? So let's just think about productions first. How are we going to produce neutrons in either group? How do we make neutrons? Perfect. So we have like a production term, right, for fission production. So I'm just going to say in both groups, we can have production. So I'm going to say production in the thermal group. And I'm also going to say production in the fast group. Because it is possible that we get a neutron born from fission with a thermal energy. It's just not as likely as it is if it's fast. So both are producing neutrons. What about some loss mechanisms? What's a loss mechanism that we're going to have in any reactor? Absorption, right? So absorption in both groups is going to be a loss. So we can say absorption. And I'm putting a minus sign just to remind us that if a term is a positive term, it means it is causing neutrons to be gained. And if there's a negative sign, that means neutrons are being lost. So because of absorption, we are losing neutrons. So we have production and absorption for infinite systems. If the system's not infinite, what's another loss that we could have? Yeah, perfect. And there's going to be leakage from both groups too. So I'm going to show leakage as an arrow going out, going like out of the group, and that's a minus sign. And we'll just say net leakage. And both groups can have this net leakage. There's only one other mechanism that we have to consider, and this is a new mechanism we haven't seen before, because this is the first time that we've had two groups. But just like we were talking about, neutrons are born fast, and they will become thermal if they scatter. If there's a scattering reaction that knocks a neutron from the fast group into the thermal group, then that's a loss from the fast group, and it's a gain for the thermal group. So I'm going to draw an arrow going from right to left for scattering, but also a thermal neutron could possibly upscatter into the fast group as well. So I'm going to draw arrows going both directions, and these represent scattering. Fast neutrons can downscatter into the thermal group. Thermal neutrons can upscatter into the fast group. So in terms of what our conservation equation is going to look like, we have all of the same gain and loss mechanisms for each group. We just have this one new term, which is representing the scatter. So these groups are going to be coupled. What are some ways that the thermal group is coupled to the fast group? Like, what can the thermal neutrons do to create more fast neutrons? They could fission, right? So that's one way that they're coupled. And then they're also coupled by scattering, because a thermal neutron can scatter up into the fast group. So these and similarly, every time a thermal neutron is gone, it produces from fission, it's going to produce neutrons mostly in the fast group. So these mechanisms, the scattering and the fission, are coupled when you have a multi-group problem. So that's the picture that we just drew. This is kind of like what I'm calling a heuristic derivation of the equation, because we're thinking about what are all the gain and loss terms, and then we're going to turn those into, turn the individual terms into equations, and then we're going to develop a whole conservation equation for each group. So within each group, we can use constant, or at least assume that there are constant material properties. So we've got like a diffusion coefficient for each group, a sigma F for each group, a sigma A for each group. Any constant that's going to appear in our diffusion equation, any like material property, you would have that value unique to each group, and I'm using subscripts for that. Ultimately, what we're going to say is that this flux overall, overall the neutrons have an energy distribution, but when we have a multi-group approximation, we're saying the flux in each group is kind of, if we were to add them all up, the fluxes in each group, it's going to give us the overall energy dependent neutron flux. So that's what this is. This is the energy dependent neutron flux, and we can say that it's just the flux in group one. And the flux in group one can vary with position and time, plus the flux in group two, which can also vary with position and time. So when we write this, phi1 is the flux of all neutrons who have energies in the E1 group, in the fast group. And then phi2 represents the flux of all neutrons that are in the thermal group. And basically, what we're saying with part 3 is that there's that fission spectrum that says what's the probability that a neutron is born with a certain energy. What we're going to do now is just say that instead of looking at it as a distribution, we're just going to say there's a fraction that we're born in group 1, or there's a fraction that we're born in group 2, and those two fractions overall add up to 100%. And those fractions are the fission spectrums for, I'm using the symbol for fission spectrum, but really it's like the fraction of neutrons that are being born in group 1 and the fraction of neutrons that are being born in group 2. And these are basically like some, you can think of them as probabilities that they have to add to give me 100%. And like for all practical purposes, x1 is probably like 0.999 and x2 is like 0.001 or something like that. X1 is going to be much bigger than x2 in reality, but right now we're just considering that they both have a value. We're not going to set x2 to be 0 just yet. So each group is categorized by these average properties. You have a flux for each group, you have a fission fraction for each group, and you have average speeds for each group too. And putting all of that together, um, if we put all that together, we can start getting formulas for each of these reaction terms that we have in each group. So that's the goal, is to take what we've done here and develop our multi-group or our two-group diffusion equation. So these conservation equations, they're going to look like rate of change equals rate of gains minus rate of losses. Um, these are all going to be rates per unit volume. And we kind of already talked about what these gain and loss terms are, right? We said that in each group, there's going to be gains due to production. There's also going to be a gain due to scattering into that group. But there's also going to be a loss from each group because of absorption. There's going to be a loss from each group because of net leakage, and each group could lose neutrons because neutrons could scatter out of one group and into the other group. So here, let's see. Um, so yeah, we have two production mechanisms for each group and three loss mechanisms for each group. So this is just explaining in words kind of what we already showed on that last slide. And so we can actually basically, the way that we've set everything up, we can pretty much use the same formulas that we had for one group diffusion to characterize what the terms look like in our two group diffusion equation. So like if we wanted to write the leakage rate, the net leakage rate density, that's going to look like a diffusion coefficient for that group. So I'm going to say D1 times the Laplacian of the flux in that group. That is our net leakage term. And I'm using subscripts 1 because it's for the fast group. So if I wanted to write the net leakage term for the thermal group, how do we think it's going to look? Same thing, but just with twos for group 2. So the net leakage rate in group 2 is going to look like the diffusion coefficient in group 2 times the Laplacian of the flux in group 2. And this negative sign is up front that's a consequence of whenever we did the substitution for Fick's law, there was the minus sign that was built into that. That's where that minus sign is coming from. What's the absorption rate density going to look like? Just in terms of like what quantities would we multiply together to get the absorption rate density? Perfect, right? It's going to look like a sigma A times the flux. And then for group 1, it's just the sigma A in group 1 times the flux in group 1. And the flux in group 1 can vary with position and time. And if you look at the units of this, right, it's an absorption rate density. So it has units of reactions per unit volume per unit time. And same thing with this net leakage term. It also has units of it's a leakage, so it's going to be neutrons per unit volume per unit time. The absorption, even though it's a reaction, it's technically also a number of neutrons because for every neutron that every absorption is associated with a neutron. So you could think of this as having units of absorptions per unit volume per unit time or neutrons per unit volume per unit time. They're equivalent. And if that's what it looks like in group 1, then we can probably see that in group 2, it's going to look like this. So that's the nice thing about going from one group diffusion to two group diffusion is that the equations that we use don't really change. We're still able to get away with treating everything as average quantities over each group. So that's these are all rate densities. And so what kind of units are they going to have? Perfect. Neutrons per centimeter cubed per second. It's a rate, so it's some quantity per unit time, and it's a density, which means it's also per unit volume. So these are also kind of answers to your quiz question, right? Because similar equation, similar kinds of terms. They all have the same units. And so those are what our leakage and absorption terms look like. And now we can start talking about those fission production terms next. We already talked about that a fraction are born into group 1 and a fraction are born into group 2. We also have like a nu F and a sigma F for each group. This is in general, if we talk about a production rate density, this is what the production rate density is going to look like in general. And now we have two groups though. So group 1 neutrons can be producing neutrons, and group 2 neutrons can be causing fissions that produce neutrons. So these terms are going to look a little different. It's going to look like the total amount of production from each group. So it's going to look like a nu F1 times a sigma F1 times a flux from the group 1 neutrons. If I only had production from one group, this would be the production from the fast group. But the thermal group could be producing neutrons too. So there's going to be a reaction rate density associated with the thermal neutrons. And it's going to look just like the reaction rate density for the fast neutrons. It's going to look like a nu F2, a sigma F2, and a Phi2. So this right here is like the total fission, this is the total production rate density, neutrons per unit volume per unit time produced in our reactor. But if we want the fraction that are born into the fast group, then we just need a multiplier on this quantity that tells us what fraction of the total neutrons that are born get born into group 1. And so that means that we just need a multiplier of chi1 on the fast group. Right? That is the fraction of neutrons that are born into group 1. This is the total number of neutrons per unit volume and per unit time that are produced. So if we hit that with chi1, that gives us the fast production rate, that rate per unit volume, per unit time that neutrons are born in the fast group. And if we wanted to write this for the thermal group, it's going to look like the exact same total production rate density, but then for group 2, we hit it with the chi2 to give us the fraction of the total that are born into the second group. So this is going to look like chi2 times a nu F1, sigma F1, B1 as a function of R and T, plus a nu F2, a sigma F2 times a Phi2 as a function of R and T. So each of these is just saying I have a fraction emitted into each group at the front times the total production rate density. So this is kind of helping us see just in terms of the math how these groups are coupled, because in group 1 neutrons can be produced from the fast group and from the thermal group, and same thing, we can have thermal neutrons born both from fast fissions and from thermal fissions. So those are our production terms. And then, so we've talked about the leakage, we talked about the production, and we talked about the absorption. The only terms that we have left to talk about are the scattering ones. So we've been ignoring scattering up to this point because we were doing one group problems. And in one group, there's no possibility for neutrons to scatter in or out of the group if there's only one group. But now we can consider neutrons getting kicked from one group into another when they have these scattering reactions. Just like with the fission spectrum, we have a probability density of neutrons being born from fission into a certain energy group. We can also characterize a probability density function that describes the probability that a neutron is scattered into the current, into some energy group starting from another energy. So we're going to define this probability density function, P of EI to EF. This is the probability that a neutron scatters from the initial energy I to the energy EF. And DEF is the energy interval. So this tells us, just in terms of words, is about the probability that a neutron scattering with some initial energy which is E sub I, has a scattering reaction, and it emerges from that scattering reaction with some new energy E sub F, um, with energy. So let me just make sure I'm writing this properly. Emerges with a final energy E sub F that is in the energy interval DEF. So that's what this probability distribution tells us. The likelihood that if a neutron comes in with some energy EI, it has a scattering reaction where it kicks out with energy, with a new energy EF. And that final energy is in some energy width called DEF. Um, so that's the function that we need to know about. And in practice, what we would do is like if we went back, if we were in the lab and we were looking at like our cold thin target experiment, we could send neutrons that had some, like if we had maybe Californium 252, or we had some neutron source that was emitting neutrons of a known energy, we could blast neutrons into this cold target. We could put energy sensitive detectors around that target, and then we could measure the energy of the neutrons that are coming off of that from that scattering reaction. And if we were to do that, we would get a graph that looks something like this. So what we're showing on the top is the probability density function with units of inverse energy. The x-axis is the final energy axis. So a neutron is coming in with some energy EI, and then it's having a scattering reaction with a cold target. So if a neutron hits something that's cold, that means that the cold target has no vibrational kinetic energy. So if a neutron scatters with a cold target, can the neutron gain any energy in that collision? No, right? The only way it could gain energy in a collision is if it was colliding with something that had more energy than the neutron does. But if the target's cold, it's only going to lose energy in the collision. So the maximum energy is just the initial energy EI. Because if you start with energy EI and you scatter into a cold target, you can only lose energy in that collision. And what we would actually see is that there is a minimum energy that we can lose. So E min is like the minimum energy that we would see a neutron coming out of these interactions with, and we wouldn't see neutrons being born with any energies coming out of these scattering events with any energies lower than this minimum energy, E min. This function, this P of EI to EF, it's a probability density function. That means that the area under the curve is 1. And if this area, if it's a PDF, that means that this area has to be 1. What does that mean about the height of this function? What does this height have to be for this area to be equal to 1? Perfect, right? It's just going to be 1 over this energy difference, right? It's going to be 1 over EI minus E min. And notice that this has units of inverse energy, and this has units of energy. And if I did EI minus E min times this difference, which is also EI minus E min, that I'm going to have energy units on the top, energy units on the bottom that are going to cancel and give me an area of 1. So that's what this probability density function is going to look like. And if we knew what this function was, like if we had an actual functional form for it, then we could use it to predict the fraction of neutrons that are coming out of a scattering event within some energy interval, say from E1 to E2. So if I know this probability density function and I want to use it to find the probability or the fraction of neutrons being born coming out of a scattering event with this energy range, how would I set that equation up? If I want to find like a probability from a probability density function. If you have a probability density function and you integrate it over the whole interval, what do you get? You get 1 or 100%. So if I take any probability density function and I integrate it over the full range of values, I get a fraction which is 1 or 100%. So if I just integrate it over some range, then that's going to give me the probability of the event happening within that range. So I'm going to integrate from E1 to E2 of my probability density function that goes from EI to EF D E F. So if I knew what this function was, I could carry out these integrals and then I could use them to get the fraction that were emitted in some range. And so like if I knew the energy range of my group was say from 0 to 1 eV, I could integrate this function from 0 to 1 eV, and that would give me the probability that neutrons are scattering into the thermal group. Okay, so that is kind of like the preliminaries that we need to understand the scattering term. So that's why I'm talking about this. Um, in general, the scattering cross-section, it is going to depend on the energy of the neutron that is causing the scattering event. So it depends on the incident neutron energy. And that was what we were calling EI, the incident or the initial energy. And if we have this scattering cross-section and we multiply it by this probability that my scattering kicks me from one energy to another, this product has a very special name. Um, and what it represents is this cross-section for scattering from some energy EI to some energy EF. So the probability for scattering from energy EI to EF, where this is occurring in some interval D, E, F. Let's think about the units of this quantity just to make sure everything makes sense. What would be the units of a sigma S, of a scattering cross section? Perfect. Yeah, we can say reactions per centimeter. We can say reactions per centimeter. This probability density function, what are the units of the probability density function? It's a density, so it's 1 over something. It's a probability that characterizes going from some energy to some other energy. So in this case, it's a probability in the energy variable. So it's a probability per unit energy. And then DEF, that is also an energy interval. So it's also, DEF is going to have energy units as well. So if I were to multiply all three of those, like look at the units of each term, these electron volts cancel those electron volts. So this overall product represents a macroscopic cross section. At least it has the same units as a macroscopic cross section, but it's describing the cross section that gets you from some energy EI to some energy EF. So, but it has the same units as any other cross section, centimeters to the -1. And you could say reactions per unit centimeter. Those are both fine ways of saying that. Um, so that is, if we multiply all three of those things together, that's just a cross section. We give this product though, the cross section times the density function, its own symbol and its own name. So if you ever see a sigma S going from EI to EF, what it means is that you have the cross section at some initial energy, and it's being multiplied by a probability density function that's characterizing the chances that you're scattering from some energy EI to some new energy EF. This quantity right here in nuclear engineering, it has its own special name. This is called the macroscopic differential scattering cross-section. So it's kind of like a cross-section, but it has extra units because of this probability density function. What are the units of this sigma s times this probability density function going to be? Per EV as well, right? Because we also have the density function hitting the cross section. So its units are going to look like inverse path length, inverse length per unit energy. Right? It's kind of like if up here, if we just grouped those two terms together, right? If I just group those two terms together, then the units, I would also still be picking up the per EV units because they're attached to my probability density function. So for example, this might look like 1/centimeters times EV. Or you could say reactions per unit distance traveled and per unit neutron energy. And that name sounds weird, differential scattering cross section, but if you integrate it over all energies, then if you integrate it over all final energies, right? That's what this integral is. It's over all final energies. So when I replace the macroscopic differential scattering cross section with the normal scattering cross section times the density function, the normal scattering cross section only depends on the incident energy. It doesn't depend on the final energy. So when I carry out this integration, the sigma s of EI is just like a constant with respect to the final energy. So it comes out of the integral. And then I'm integrating this probability density function over all energies. And we know that the integral of a probability density function over the whole domain is 1. So therefore, this is just going to return me sigma s at EI. And that's why it's called a differential scattering cross-section, because if you integrate it, you just get the regular scattering cross-section. So hopefully that's okay. This is what we need to know about this differential scattering cross-section so that we can start characterizing our scattering terms. So in the two-group model, we can talk about this in a way that's kind of similar to what we did with the fission spectrum, where we can look at this probability as just a fraction that we get scattering from one group into another. So we can write these differential scattering cross sections as just, so if I want the cross section, the differential scattering cross section to go from group 1 into group 2, it's going to look like the scattering cross section for group 1, which I'm going to write as sigma S1, times some little probability, some fraction that I scatter from group 1 into group 2. And similarly for the group 2 differential scattering cross section, it's going to look like the cross section for that group times the probability that I grow from the other group into that group. And there's a slight difference in notation. This p is a lowercase p. It is a probability. It's you've already integrated over the energy. The p on the previous slide was a capital P. It was a probability density function. Here I'm trying to kind of merge the notation in two different resources because Svetkov uses a slightly different notation than Adams does. But so whenever you see a little p, this is the probability or the fraction. So that's what this is representing. It's just the fraction. You've already integrated over the energy range. So the p1 to 2 and the little p2 to 1, those are the fractions of neutrons that go either from these are actually backwards because 1 to 2 is from the fast group into the thermal group. And then, so, sorry, there's a little typo here instead of bother mode. I have my ones and my twos basically mixed up, right? 1 is the fast group, and 2 is the thermal group. And then this is also backwards because this should be thermal. 2 was the thermal group and 1 was the fast group. Sorry about that. Hopefully that's the fix that we would want to make. Those were just backwards, and the indexing tells us which one is which, and I just put it backwards there. So sorry about that. So yeah, P from 1 to 2 is the probability that you go from fast to thermal when you scatter. P2 to 1 is the probability that you go from thermal to fast when you scatter. And if we have these multipliers, then we can get the scattering rate density, knowing the cross-section and knowing the scalar flux. So an outscattering rate is just going to look like a differential scattering cross-section times, or sorry, this is, let me just go back real quick. So ultimately, when we talk about the cross section to go from EI to EF in DEF, it's the cross section times the probability density times the energy interval. What we have in those terms is we're doing a cross section times a fraction. So the PEI to EF times the DEF is like the fraction. And so we've got our scattering cross section to go from one group to another. And if we hit that with the scalar flux, that'll give us the scattering rate density. So this is just going to look like the cross section. If I'm out scattering from the fast group, it means that I'm going from group 1 into group 2. So this is going to be sigma s from 1 to 2 times the flux of the neutrons that were corresponding to the initial energy. So if I'm going from 1 to 2, it's going to be based on the flux of neutrons that are in group 1. Neutrons in group 1 have scattering reactions that could kick you into group 2. So that's what the outscattering rate density looks like for the fast group. And then the inscattering rate density is going to look similar, but it's it's inscattering. So we're going from another group into this fast group. We're going from group 2 into group 1. And if we're going from group 2, it's going to be based on the flux of neutrons in group 2. So those are what the outscattering rate density and inscattering rate density terms look like for the fast group. And if we were to write the thermal group, it's going to look very similar, except they're actually just going to be flipped, right? Because the outscattering means that I'm going, if I'm outscattering from group 2, that means that I'm going into group 1, right? So this is going to be the scattering from group 2 into group 1. If it's going from 2 to 1, it's going to depend on the group 2 flux. So that's what I would have for group 2, the outscattering rate for group 2. And then last but not least, the inscattering rate going into group 2. To get into group 2, I have to come from group 1. So this is going to look like sigma s to go from 1 into 2. And if I'm starting in group 1, it's going to be based on the flux of neutrons in group 1. So hopefully that's all okay. Oh, question?
What's only based on?
Ah, good question. Technically, I should include my time here. Thank you. Yeah, that's just I was keeping time arguments the whole way, and then for some reason when I was making my notes for this slide, I just left it out. But you're right that it should stay there. Already. So those are all of our scattering terms. And there's another scattering that we are kind of ignoring, which is within group scattering, like because you could just have a scattering event that doesn't kick you out of your current group. But what we are going to do is just assume that all scatterings do remove a neutron from the group. So that means that there's no within group scattering. So the cross section from going from group 1 into group 1 is equal to the cross section from going from group 2 into group 2. And we're saying that that's just 0. We're ignoring in-group scattering. And so ultimately, we already talked about what all of the production and loss terms are. And our conservation equation is going to look like rate of change equals rate of gains minus rate of losses. And we've already developed what the production terms are, what the in-scattering and out-scattering terms are. We know what the absorption and the net leakage terms look like. So the only other extra term is the change rate density, which is just looks like it the same way that it does in the diffusion, a one group diffusion. It's 1 over your group speed times the time derivative of that group flux. So that's my rate of change. And then I have all of my rates of gains and my losses on the right side. And so this is what the equation, if I take all of those definitions and sub them in to this general conservation equation here, this becomes my group 1 equation, and this becomes my group 2 equation. So we took advantage of conservation. We looked at all of the production and losses that we could have in this context of a two-group problem. We worked out mathematically what all of those gain and loss terms are, and then we used conservation to develop a mathematical equation. So this is what we would call the two-group diffusion equation. This is the same equation. I just want to talk a little bit about it. So if I were to solve this equation, I'm getting two functions. I'm getting a function phi1 and I'm getting a function phi2, but phi1 and 2 appears in both equations, right? Equation 1 has phi1 and it has phi2. And same thing with equation 2, it has phi1s and it has phi2s. So these are coupled partial differential equations in the variables phi1 and phi2. But if you were to write these equations down, and then if you spelled out all of your like boundary and initial and physical conditions, then you would have a completed model and you could start moving forward to proceeding and solving the model. So these equations are coupled, and they're coupled because the fission and the scattering process links neutrons in each group. So like, notice that this production term in group 1 is basically similar to the form of the production term in group 2, but it's just that there's a different fraction of neutrons being born in group 1 and group 2. But what's happening in group 1 affects what's happening in group 2. And what's happening in group 2 is affected by what's happening in group 1 because of fissions being born into both energy groups and possibly being caused by neutrons that started in both energy groups. But then there's also coupling between the scattering terms. And notice that the in-scattering term for group 1 is equal and opposite to the out-scattering term from group 2. And that hopefully makes sense from the picture that we drew, because those arrows were going back and forth. And so anytime that one group was losing neutrons because of scattering, the other group was gaining them because they scattered into that thing, right? So just like in group 1, there's a loss term because we can have outscattering from group 1 into group 2. But then in the group 2 equation, that term is a gain because every time that something scatters out of group 1, it ends up in group 2 and is a production on the group 2 side of the equation. So that's hopefully helping us see how these equations are coupled and how these two physical processes, fission and scattering, lead to that coupling. The next thing that we could do is we could just say, okay, I want to design a critical reactor using the two group model. And if I want to design a critical reactor, it means it's got to have a steady state configuration. So generally, like if a reactor is critical, it's running at a steady state, same power for a really long time. That means no derivatives with respect to time. And also if there's if I want to make a steady state problem, that means the time derivative goes away and now nothing depends on time. So I can drop the t arguments on all of my flux terms. So going from here to here, all I've done is I've assumed steady state. And that gives me the steady versions of these equations. And if I think about the eigenvalue problems that we talked about with one group diffusion, we can cast these equations as eigenvalue problems, where we basically say we have production terms, which is the production due to fission. We have these loss terms due to due to net leakage and due to absorption. We also have these scattering terms, but those terms are, it's almost like they're transfer terms instead of, if I were to look at the entire reactor, if I were to add these two group equations together, then all of the scattering terms would actually cancel because they're equal and opposites on each group. So like when we talk about the K effective, it's a it's for the entire system that we're considering. So if we add these two groups together, then the scattering terms don't really form like a production or a loss. So ultimately, if we cast our equation as a production loss operator problem, then the K effective, the 1/K effective is hit on the production term, and then the other remaining terms constitute like the loss for each group. So this is how you go from this is how you get the K eigenvalue forms of these two group equations. So these equations look basically the same. It's just that we're throwing in a 1/K effective on the fission production term. And so this is also aligning us with the class notes. These two equations are expressed in Dr. Spetkov's notes as 4.1.22 and 4.1.23. So, okay. And that is basically what I wanted to say for today. So that gets us to a point where based on what we've done so far, this gets us like a long ways through what we want to say about chapter. So when you look at homework 3, you're going to see some stuff that's about reflectors, and then you're going to see some stuff that's like energy dependence and multi-group stuff. At this point, you can do any of the stuff involving reflectors. And after class next time, I'll talk about the last things. I'll get us through the rest of the multi-group stuff so that we could have everything we would need to finish and understand what's going to be on homework 3. And I apologize, I haven't posted homework 3 yet. I just have to do a couple more edits before I post it. I'll make an announcement once it's uploaded into Google Drive and you'll see it on Canvas. Expect to see that in a couple hours. I'll have that for you. And yeah, I'll try to get your quiz 2 and 3 back to you next class as well. If y'all have questions, please let me know. And yes, sure. Let's see. Oh, okay. No worries. This one?
Yeah.
Yeah, if y'all don't have any questions, have a good rest of your day, and I'll see y'all in class on Thursday. Mhm.
With the testing center.
Oh, yeah, I have some emails about that. I still need to get that sorted out. Yeah, thank you for asking about that. Because I haven't done anything with the testing center, I still need to talk to them and figure out exactly what that process is going to look like. What I was expecting is that it's going to be open in the testing center on our exam day. So that whenever you so that yeah, that ideally I think it's going to be set up so that that Thursday it's there in the testing center. You'll have your window that you'll have your time, allotment that you can use to take it, and it'll be there for you during the testing day, so that you can go in and take it.
Okay, I just wanted to make sure and bring it up, so
Yeah.
it didn't.
Yeah, I wanted to make sure that I was, that's the other thing I have on my agenda for today is making sure that I get all the testing center stuff sorted out.
Thank you.
Mhm. Hey, oh, okay.
On the day, so you don't also show up for class that day.
Yeah, you don't have to show up for class. What you would probably like, if I was in your shoes, I think what I would probably do is just show up at the testing center around the same time. You don't have to do it that way. Like, I think I'll have it the way I haven't done it yet, but what I was assuming I was going to do is have it in there for basically like if our class starts at 10, so I would have it from 10 till close. That way, if you needed, if something happens, as long as you're taking it during that day, it should be fine.
Yeah, I didn't see, fill out the form yet.
Gotcha.
for it.
Yeah, I'm gonna do that today.
Wonder- Okay. So I'm assuming it's just pencil or it's with nothing else.
Yeah, you just need something to write with.
Every-
Yeah, you'll be given the exam. The exam will have the formula sheet stapled to the back. Yeah.
I just didn't want to put anything incorrect when I was about to submit to
Gotcha.
my request
Okay, yeah, that sounds good.
to, put a note on this.
Uh-huh.
Get next week.
Oh, yeah, yes, let us go, here, let me just pass that back here right now.
Have a good one.
Thank you, you too. Hey,
On first homework, I have some like comments back in question 7 about like redoing question 7 and then sending to TA.
uh-huh,
And I was gonna do that, but about like Janet's doesn't work. I was just wondering if we could like find what the issue is,
oh, sure.
how to get like the phone this was we downloaded the latest version, but then whenever I click on the application. That's like the error. And I tried this on like another like PC as well, and I get that feedback same thing. No, it's- and it turns like I was really confused.
That's weird, because mine does a similar thing where it doesn't come up like the first time, hmm. Oh, do you have Java installed?
I
Okay, that's fine. Because I know that it's on this Java to do this.
Probably, more time.
Oh, yeah, no, you probably. Oh, you gave me more than I wanted.
For which one?
Oh, number two.
I think that was.
Well, it's just asking about the critical conditions, so just what makes like k equals 0, or k equals 1. Just like the middle, it's just the, I think a lot of people go, oh, yes,
That's critical.
but yeah, if you give me more, I'm not gonna do that. But it just meant that you, in terms of like the time. Okay, perfect. Yeah, it was just a Java thing, which I'm glad it was just that, because that's pretty easy to fix. Yeah. Yeah, I told the TA to let you know that as long as you just do the yeah, just do that problem and then email him and he'll give you the points back. Yeah. Sorry that you had troubles with the Janice. How's it going, Jake? I saw that you did good on the homework. Congratulations. Like you got the high score so far. I haven't checked in a while, but last time I checked, you got the high score. Oh, no worries. You're welcome.
Sorry about that. Comment there. I was just saying, I'm shocked to be don't think I do that. But I did have questions on questions part of the definitions.
Mhm.
For number one, for the effective, it's general mathematical form.
Mhm.
Are you wanting us to?
In terms of operators,
equation,
yeah. Mhm.
Where it's K flux is equal to L negative to -1.
If you wanted K just in terms of operators, it would just be like production over loss.
Okay, that's what I was wondering, because I didn't. I think it's stated with the yeah. Yeah, I didn't know if you meant the full operator or just, I assumed it was just the LMP.
Yeah, it was more like, I think in lecture, it might have been even been in lecture.
There wasn't lecture
two.
2, but it
Yeah.
was more of the production over loss.
Right. So the only distinction is that that's how you can write the diffusion equation as an eigenvalue problem, whereas the fundamental definition of K effective, at least one of them is just like production over loss.
Oh,
But then those are kind of linked because the more detailed way to write K effective is L inverse, the L inverse
the L
P.
inverse P, and that's what I was wondering, because like, yeah, you were saying the fundamental mode is K effective is the largest eigenvalue of that to be positive with a fundamental equation. You wanted
Yeah, that's one of those ones where there's a lot of like, there's multiple ways that you could write it that are correct. So yeah, as long as you're writing along the lines of what I was looking for, it should.
it was just big because I saw operators and I was didn't know meant that or the full